Assalamu alaikum. Welcome, students. I hope you guys are good and healthy. Now, let's start our discussion from where we left off in the previous lecture. In the previous lecture, we define control system and then we look into the different configurations of a control system. Now, today's topic is the analysis and design objectives. The word analysis, as we discussed in the previous lecture, is the process by which the system's performance is determined or evaluated, and the word design represents or describes the process by which the system's performance is created or changed. Here we have three major design objectives. One is the transient response of the system, second is the steady-state response, and third is the stability of the system. When we discussed the example of elevator, we commented that if an elevator takes too much time to reach its destination, then the passenger will get impatient, and if an elevator moves too fast, reaching its destination in comparably less time, the passenger will get uncomfortable. This journey of elevator towards its destination is called the transient response. So we can say the designing of appropriate transient response is very crucial. Sometimes this appropriate design comes through the experience also, as we have to design the transient response midway between too fast and too slow. This is too slow and sorry, too fast. This represents, I can say, impatient response, and I can also write it as uncomfortable response. So this midpoint may come through years of experience the company has spent in deploying the project. Transient response is also important for physical reasons, as too fast response can damage the physical structure permanently. In this course, we will establish a quantitative definition for a transient response. We will then analyze the system for its existing transient response. Finally, we will going to adjust the parameters or design components to yield a desired transient response, which will be our first design objective. Uh, Another analysis and design objective focuses on the steady-state response. This response is what remains after the transient response has decayed to zero. So it resembles or must resemble the input to the system, which is the desired response. We are concerned about the accuracy of the steady-state response. For example, in case of elevator, the elevator must be level enough with the floor for passengers to exit safely. So the accuracy of steady-state response is the important parameter for the design and analysis of the system, which can be evaluated through steady-state error, as discussed in the previous lecture. In this course, we define the steady-state error quantitatively. We'll analyze the system's steady-state error, and then we will design corrective actions to reduce the steady-state error. The next analysis and design objective is the stability. Uh, to understand this stability, let's start from the fact that total response of sorry total response of any system is equals to the natural response plus uh, the force response. Uh, when you studied the linear differential equation in the course of calculus, I suppose, you might have calculated the homogeneous solution and particular solution of the equation. The homogeneous solution describes the natural response, and particular solution describes the force response of the system, as the linear physical systems can be described by the linear differential equation. Natural response of the systems describes the way uh, the system dissipates or acquires energy. Hence, this response is dependent on the system and not the input. On the other hand, the force response of the system is dependent on the input applied to the system. For a control system to be useful, the natural response of the system must eventually approach to zero, thus leaving behind the force response only. In a system where a natural response grows without bound rather than diminish to zero, the natural response is much greater than the force response, and the system is no longer in control. This condition of instability might lead to self-destruction of the physical system if limit stops are not part of the design. For example, the elevator would crash the floor if the design is unstable. So we can define the stable system as a system uh, whose natural response uh, approaches or decays to zero as time approaches infinity. Uh, in a time response plot of the system, you can see the transient response is directly related to the natural response of the system, and the steady state response of the system is related to the force response of the system. Here, this is transient part, or also known as natural response, and this is the steady state or sorry force response. So, and this represents input. So I can say the transient response is also known as the natural response of the system, which is dependent on the parameters of the system only. And the steady state response is also known as the force response of the system, and which is solely dependent on the input or the forcing function applied to the system. So When evaluating the stability of the system, we are concerned about the natural or transient response only, since the stability is dependent only on the nature of the system. Now, that was all about the topic. Now, let's move on to the next topic, the design process. There exist uh, various physical systems in which the control theory can be applied. For example, mechanical systems, uh, electrical systems, and electromechanical systems, and thermal systems, uh, hydraulic systems, and etc. There are various fields in which the control system or control theory can be applied. We will restrict our discussion to these three systems: mechanical, electrical, and electromechanical systems. The first step in the design process is to create a schematic of a physical system by observing the interconnection of basic elements of that physical system. For example, if the system is electrical, then the basic elements are resistance, capacitance, or inductance. Or if the system is mechanical, then the basic elements for the mechanical systems are mass, damper, and spring. The designer must make some approximation about the system or neglect some phenomena, otherwise, the resulting sketch will make it difficult to extract the useful mathematical model in the next step. The second step in the design process is to develop a mathematical model or block diagram of schematic. The designer uses physical laws such as Kirchhoff's law or Newton's laws for mathematical model along with simplifying assumptions. Uh, these laws are Kirchhoff's voltage law, which states the sum of voltages around a closed path equals zero. And Kirchhoff's current law states that the sum of all the currents flowing in or out of the node is zero. Now, the Newton's law states that you guys must be familiar with this law. the sum of forces acting on a body equals zero if the condition is the body is in equilibrium. So we will be using these three laws to convert a schematic into a mathematical model. These mathematical model describes the relationship between input and output of the physical system. Now, the third step in our design process uh, is to reduce the mathematical model or block diagram into a simplest possible mathematical description that will only contain the input and output. This is, of course, a mathematical process. We will see how we can do it. The last step in our analysis and design process is the last process in the design process is to analyze or design the system, whichever required. This is also a mathematical process. Now, there are some test inputs that are used to verify the design of the control systems analytically instead of uh, testing the control system by applying the arbitrary inputs. The designer uses standard test inputs. These test inputs are impulse, step, ramp, parabolas, and sinusoids. The plot of their waveforms are this is the plot of impulse input. Mathematically, I can write the impulse input as sigma of t is equals to infinity for very short period of time for 0 less than t less than 0 less. Of course, making this spike physically is impossible, but we can make this impulse input as close as possible physically and 0 otherwise. The area under this impulse signal is 1, that is 0 minus 0 plus sigma of t dt is equals to 1. Uh, an approximation of this type of waveform is the application of sudden spike or jerk of energy to the system. The response due to this input is the transient response only, since the waveform does not exist after just after t greater than 0 plus. So the response is only the transient response of the system. So designer can use this test input to drive a mathematical model of the system. Since mathematical model is only related to the transient response or natural response of the system. The second input is the step input. The waveform is S, symbol is uh, mathematically I can write as u of t is equals to 1 for t greater than 0 and is equals to 0 for t less than 0. Uh, this step input represents a constant input or command to the system. This constant command can be position or velocity or temperature or voltage or any other physical input depending on the type of the control system used. This is the most widely used input applied to the control system. The designer used this input to study both the transient and steady state response of the system. The next input is the ramp input. The waveform of the ramp signal is f of t, and this is time. Mathematically, I can write it as t u of t for uh, sorry t for t greater than 0 and 0 for t less than 0. The ramp input represents the linearly increasing command. This input can be used to test the tracking ability of the system for changing input and reveals the additional information for steady state error, which will be discussed in the upcoming lectures. Now, the next input, test input, is the parabolic input. The waveform of the parabolic input is like this. Mathematically, I can write f of t is equals to 1 by 2 t square for t greater than 0 and is equals to 0 for t less than 0. Huh. The same description which we use to describe this input can be applied to this input also. Uh, These input can also be used to determine the tracking ability of the system. Now, the final test inputs are the sinusoids. Waveform is like this. Mathematically, f of t is equals to sine omega t. Omega represents the frequency of the wave. Now, sinusoids are also used as the test inputs. They are used to drive a mathematical model of the system. We will discuss it in the upcoming lectures. Now, that was all about the design process of the system. Now, let's do a simple case study. Uh, we have a variable resistor called the potentiometer as shown here. The resistance is varied by moving a wiper. This wiper is movable. Uh, the resistance from A to C is fixed. but the resistance from B to C is variable since the wiper is moving. Uh, what we are required is to draw a block diagram of the potentiometer showing the input variable, the output variable, and the gain, which will be inside the block. And this is the constant by which the input is multiplied to obtain the output. So here we have to find out the potential difference between point B, which is the wiper arm, and the ground. So let's do it in a separate sheet. Uh, we have to find a constant K, uh, which when multiplied with input, which is theta of t, as shown here, uh, we get V naught of t. In a block diagram, I can represent this as a constant K, input which is theta of t, and output which is V naught of t. Now let's find out the potential difference potential difference between point A and C is 50 minus 50, which is 100 volts. Uh, and here it is written, it takes 10 turns to move the wiper from A to C. So it takes 10 revolutions to move revolutions to move from point A to C. So we can write K is equals to this 100 volts divided by the total number of revolutions that are required to move from point A to point C. Since we are considering the potential difference between point A to point C, so we will have to consider the total number of revolutions required to move from point A to C. So we have 10 revolutions. Converting it in the degrees by multiplying it with 2 pi, we will get the answer 1.9. So the constant factor uh, with which the input is multiplied is 1.59. In a block diagram, I can represent this as this way, or mathematically I can write it as V of t is equals to 1.59 theta of t, sorry, So this is the uh, answer of our case study. Now let's move on to the second chapter, which is modeling of a system in frequency domain. Modeling represents here a mathematical modeling actually, which means writing mathematical equations for the inputs and outputs by applying physical laws as discussed in chapter 1 in the topic of design process. Mathematical modeling, as discussed in chapter 1, it can be done in either frequency domain or in time domain, both of which are part of the course, fortunately. In this chapter, we will model a physical system in frequency domain. As discussed in chapter 1, that we will use Kirchhoff laws in case of electrical system and will use Newton's laws in case of mechanical system. Both will yield actually the differential equations yielding so relating input and output after their application, which actually are time domain differential equation in specific. So we need a tool that can convert those time domain differential equation to the frequency domain equivalent. The mathematical tool used for this purpose is the Laplace transform. The Laplace transform, or the also known as the Laplace integral, uh, can be described as the Laplace transform can be represented as f of s is equals to 0 till infinity f of t e power minus st dt, where f of t is sorry time domain function that we want to convert into the frequency domain. Uh, this e represents here the exponential function. You guys might be familiar. In case any one of you don't know that, uh, this S represents the sigma plus j omega, which is also known as the complex frequency. So we can use this tool to convert any time domain function represented by f of t into its equivalent frequency domain function represented by capital F of s. Just as a side note, control system is a mathematical course majorly, and in my opinion, mathematics is a tool for engineer at least. So you guys need to do a lot of practice to be comfortable with it. Uh, that's what a technician do to master the tool in industry. Uh, no matter how easy the mathematical problem look, you must try it yourself to see if it's working for you. Uh, After spending some years in here teaching and interacting with my students and my fellow colleagues and my classmates, I can say that this course is very crucial if you want to study engineering abroad specifically. So I suggest you to try every problem we do here. That's kind. I think that's enough motivation, I suppose. Now let's do a simple problem that will describe how to use the Laplace integral. Question is find the Laplace sorry transform of f of t is equals to e exponential minus at u of t. This u of t represents the step input. So applying Laplace transform integral on both sides of equation. So this will become f of t e minus st dt 0 till infinity is equals to, we are taking Laplace transform on both sides of this equation, and this will become 0 till infinity a e minus at e minus st dt. The value of ut is equals to 1 after t greater than 0, and we are using this integral from 0 till infinity. So the value of the step input will become 1 after t greater than 0. So simply removing it. Now solving this integral, this is with what we can write it as f of s. Any time domain signal, taking Laplace transform of any time domain signal will make it its equivalent frequency domain signal represented as capital F of s. It's just a convention to write capital notations with frequency domain variables and write small letters for time domain functions or signals. So this E and this E uh, are multiplying, so their powers will get added. So 0 till infinity, taking out this a outside of integral t minus s plus a t dt, taking integral of this function, it will become a of s plus a minus sign e minus s plus a t, sorry, the limits of the integral. The integral of exponential is also the exponential. So putting the limits in the exponential function minus a of s plus a. This will become e minus infinity and minus it will become e power 0 which is equals to 1. Now e over minus infinity can be written as minus a over s plus a e infinity minus 1, and e power infinity is infinity and 1 over infinity is 0. So this term will become 0. So multiplying it with this term, so the answer will be a of, sorry, a of s plus a. So the Laplace transform of the given function is a over s plus a. I think that's enough for today's lecture. Uh, now we will start from here in the next chapter. Uh, Take care. Thank you.